Welcome to the Deep Dive, the place where we take the most complex, cutting-edge technical documents and turn them into the knowledge you need, fast.
You, the learner, have handed us the blueprints for what looks like the next era of massive machine learning, and we're here to give you that efficient, detailed understanding you're looking for.
That blueprint is a system called Pathways.
It is. And, the rapid progress of machine learning is now entirely characterized by this really fierce coevolution.
Coevolution, how so?
Well, the models get bigger, the underlying hardware, TPUs, GPUs, all these specialized accelerators, it gets faster and faster.
Your software has to keep up.
Exactly. The system software that orchestrates it all has to adapt at lightning speed.
And when you look closely at the source material for this one, it becomes really clear that a lot of the older systems, the ones built for yesterday's dominant models, are now fundamentally restrictive.
They've hit a wall. So Pathways isn't just an incremental update. It's an entirely new system, and it's explicitly designed to break those limitations. The whole point is to enable research into future, immensely complex workloads that, frankly, just weren't possible before.
So our mission today is to go deep into the mechanics of that. We're diving into the Pathways architecture. We're going to explore its novel single controller design.
And we'll scrutinize the critical data structures, like the sharded dataflow graph, which solved a massive scaling crisis.
Right. And we'll analyze the fascinating algorithms it uses. We'll be focusing specifically on how it achieves state-of-the-art performance while supporting these new heterogeneous ML models.
Oh.
All right, so let's unpack this. If you're going to build a completely new orchestration layer from the ground up, you have to be solving a colossal engineering problem.
You do.
What was so fundamentally limiting about the old way of doing things that necessitated this whole ground-up rebuild?
The crisis, it really boils down to a conflict between simplicity and flexibility.
Okay.
And to understand it, we have to start with the dominant model today. Single program, multiple data.
All right, SPMD.
SPMD.
It's what most people think of when they imagine training some massive model. A highly synchronized, almost, militaristically disciplined cluster.
That's a great way to put it, exactly. Most current state-of-the-art ML workloads, they rely heavily on this model. And it often finds its roots in, classic high-performance computing standards like MPI.
So what makes it simple?
The simplicity is its strength. All accelerators, whether you have 8 on a single host or 2,000 across a whole cluster, they run the exact same computation.
In lockstep.
In perfect lockstep.
And because they're all running the same code, the communication must be highly predictable.
Precisely. Communication is handled by these simple, really well-defined collective operations.
Like all reduce.
All reduce is the classic example. And the massive advantage, particularly in what we call multi-controller systems like modern JAX, is just raw performance. Since the client code runs identically on all the local hosts, dispatching computations only involves communication over these extremely fast local interconnects.
So like PCIe or some other high-speed internal fabric.
Right, and this results in incredibly low latency for starting the kernel on the accelerator.
So it's fast. That low latency is fantastic, but we're seeing a major shift in model design, aren't we?
We are.
So what are the emerging workloads that are starting to absolutely shatter that rigid lockstep constraint of SPMD?
The sources, they really highlight 3 major trends that are forcing the change. And they all point towards heterogeneity and dynamic complexity.
Okay, let's take them one by one. Let's start with the first one you mentioned, pipelining.
Right. So for these massive language models, especially complex transformer architectures, the sheer size of the model parameters means you can't just use pure data parallelism anymore.
The model is just too big.
It's way too big to fit in the memory of one or even a handful of devices. So researchers have to engage in aggressive model parallelism, or what we call pipelining.
Which is where you split the model itself into pieces.
Exactly. The model gets split into successive stages, let's say 16 different layers. And those stages run across different devices, or different groups of devices.
So the devices are no longer running the single program. Device A is running stage 1, device B is running stage 2, and so on.
And that's the core break from the traditional SPMD lockstep.
Right.
Device A might be calculating an attention layer, while device B is over there calculating a feed-forward network. They have to coordinate the passage of all these intermediate tensors.
Which requires more complex asymmetric communication than just a simple collective operation.
It's a whole different ballgame.
Okay, which brings us to the second, and I think arguably the most critical trend for the future, computational sparsity.
This is where we move completely out of SPMD and into the realm of multiple data, or MPMD.
So what does that look like in practice?
Well, models like the mixture of experts, or MOE, they don't utilize all their parameters for every single input example.
Okay, so it's not a dense calculation.
No, not at all. Instead, based on the input data itself, they use a learned function, they call it a router, to send the data to a specific dynamically chosen subset of expert networks.
That's fascinating, but I can already see how that introduces a profound systems challenge.
It's a huge one. The computation across the accelerators, it has to become heterogeneous and data-dependent.
So you can't predefine your communication patterns.
You can't. You have no idea which device will need to talk to which expert until the data itself arrives and gets processed by that router.
And this dynamic routing, it just renders the fixed, one-size-fits-all collective communication of SPMD completely obsolete.
Gone. It demands a system that's capable of efficient, fine-grained control flow and dynamic, sparse data exchanges.
That sounds like a system that requires a high degree of centralized, intelligent control. Which sort of brings us to the third trend you mentioned, cluster heterogeneity and islands.
Yes. Modern machine learning clusters, they're organized into these tightly coupled islands of accelerators. You often hear them called TPU pods.
And they're connected by these ultra-fast internal interconnects, like the ICI.
Right, but these islands, they're connected to each other over a standard, much slower data center network, the DCN.
Okay, so you've got these high-speed zones linked by slower highways.
Precisely. And providing exclusive access to a single, giant, homogeneous island is incredibly expensive. And honestly, it often leads to a lot of resource waste.
So researchers need more flexibility.
They need the flexibility to map a single computation across multiple, smaller, and more readily available islands.
And the old SPMD architectures, they just can't do that. They assume you own one big piece of hardware.
Right. They generally assume exclusive ownership of one large, homogeneous slice of the hardware. So Pathways, it had to be built with the ability to manage and virtualize resources across this whole distributed, interconnected landscape.
That immediately points back to older, more general-purpose systems like, say, the original TensorFlow V1. I mean, it did offer flexibility and resource virtualization, so why didn't those systems succeed at scale? Why couldn't they just be fixed?
They had two fundamental flaws, and they were really difficult to architect away. The first was performance, and the second was a scaling crisis in how they represented the computation.
Let's talk about the performance flaw first. Why was its centralized single-controller architecture just too slow?
Well, in that general distributed data flow model, the single client that was responsible for orchestration was conceptually and physically farther away from the accelerators.
Further away.
Dispatching any accelerator computation, even a tiny one, required sending instructions over the data center network. And we're talking about DCN latency versus the local PCIe or ICI latency that's used by multi-controller SPMD systems. This DCN communication latency is typically an order of magnitude slower.
A whole order of magnitude, that's a critical difference. I mean, if you picture a modern pipeline where you have hundreds or thousands of these tiny steps chained together, if every single step requires waiting on DCN latency before the next instruction can even be issued,
The accelerator starves.
the most expensive piece of hardware just sits there idle, waiting for its next task.
Correct. That host-side bottleneck, where just dispatching the next step takes too long, made TFV1 utterly unsuitable for pipelined or fine-grained computations. All the host-side preparatory work at the destination would only trigger after that slow cross-network transfer of data and control messages finally completed.
Okay, and the second fatal flaw, the scaling headache. The one related to how it represented the computation graph. This is a brilliant technical detail that Pathways really had to solve elegantly.
It was a catastrophic scaling issue. TFV1 required materializing the full sharded computation graph.
Full graph.
The whole thing. Think about it. If you have an operation that takes an input that's sharded, say, in dollar ways, and it produces an output that's sharded in null ways,
Okay.
representing all the edges of communication and dependency between those shards requires nuller times and dollar edges in the graph representation.
Okay, so if nuller and nuller are, say, 128 cores each, that's 128 squared over 16,000 edges just for a single logical connection.
Now, scale that up to the thousands of cores you need for modern trillion parameter models. When the number of shards reaches into the thousands, that $1 times $1 in calculation, it just rapidly explodes into millions of graph edges.
And the system just grinds to a halt.
It spends unacceptable amounts of time just in graph serialization, memory consumption for the graph structure, and then execution planning. It became entirely unwieldy and unsustainable.
It's interesting, this really echoes systems engineering problems we saw in, the database world decades ago.
How so?
How do you reconcile the need for global consistency, which a single controller gives you, with the demand for breakneck distributed speed, which multi-controller systems offer? It feels like history repeating itself, but just scaled up to the capacity of TPUs.
It's a fundamental trade-off. It really is. The challenge for Pathways was to synthesize the best of both worlds.
Yeah.
They had to retain the flexibility, the resource virtualization, and the global view of a single controller system, but somehow achieve the ultra-low dispatch latency and scalability that were traditionally associated only with those rigid multi-controller SPMD systems.
So they needed the maneuverability of a race car combined with the payload and persistence of a massive freight train.
That's a perfect analogy.
Okay, let's discuss how they achieved this architectural synthesis. The foundation is what the source material calls the hybrid core design. They chose the single controller path, but what specific mechanisms did they borrow from that fast multi-controller world to inject the necessary speed?
So they adopted the single controller model specifically for its flexibility, for its resource management capability, and its inherent ability to handle heterogeneity and multi-tenancy.
So that solves the what problem running complex sparse computations.
Right. But crucially, they paired this centralized control with asynchronous dispatch and gang scheduling. And these mechanisms, they address the how fast problem.
Asynchronous dispatch immediately tackles that latency issue we were just talking about, right? It ensures the client isn't stalled waiting for every single step.
Correct. The overall structure is a client-server architecture. The client describes the program, and the Pathways runtime executes it on these system-managed islands of compute.
And it can do this for many clients at once.
The runtime operates on behalf of potentially many clients simultaneously. And this clear separation, it allows the system, not the user, to manage, virtualize, and optimize the resource allocation and the execution order.
Let's focus on the centralized control aspect first. If they have a single controller, it needs to manage devices across thousands of accelerators spread across physically distinct islands. That seems like an inherent point of fragility, but also the key to effective virtualization.
It is both. The resource manager is global. It maintains centralized control over all devices across all islands.
All of them.
All of them. The centralized view is just non-negotiable for coordinating resource virtualization and multi-tenancy across a huge heterogeneous cluster.
So how does that centralized resource manager present the cluster to the client? I mean, the client isn't looking at a map of physical hardware, right?
No, absolutely not. It presents it through the concept of virtual devices. This is a classic systems design abstraction, but it's critical here. Clients do not request physical hardware. They request virtual slices of an island.
And that slice is defined by logical characteristics.
Exactly. Like a desired mesh shape, a certain interconnect topology, or a minimum memory capacity.
Why is that layer of indirection so powerful? I mean, beyond just simplifying the user's view of the world.
Well, the power lies in enabling this sophisticated cluster management that was basically impossible under SPMD. By abstracting the physical location, the resource manager gains the ability to implement future features like transparent suspender UME
Wow.
and migration of running computations.
So if a physical device needs maintenance or a higher priority job comes in, the virtual slice can potentially be paused, moved to a different physical island, and resumed, all without the user program even realizing it moved.
That's the goal.
Yeah.
This is essential for maximizing utilization and minimizing user disruption in a massive multi-tenant environment.
That moves way beyond just training efficiency and directly into cluster economics and, operational reliability. But in the present, what's the initial policy? Are they already doing complex migration?
Not yet. The initial implementation, it uses a simple heuristic, statically balancing the load and maintaining a one-to-one mapping between virtual and physical devices.
But the plumbing is there.
Exactly. The architectural scaffolding, that virtual device abstraction, is now in place to adopt much more complex dynamic allocation algorithms in the future. Algorithms that can optimize allocation based on the cumulative resource requirements of all concurrently running client programs.
Okay. Now let's move to the data structure that holds the computation together, the sharded data flow graph. This is the elegant technical fix for that monolar times nest scaling crisis of the older systems.
It really is.
So how did they manage to compact millions of potential edges into something manageable?
Well, they started by defining the core unit of computation as the compiled function.
Okay.
These functions, they're derived from high-level frameworks like JAX or XLA, and they are subcomputations. They're characterized by having known input and output types and shapes, bounded loops, and very few conditionals.
Ah. And the critical feature here is that their resource requirements, memory, compute time, can be estimated in advance.
That's the key. Knowing the size and shape of the operation before you run it is absolutely key to avoiding bottlenecks.
Hmm.
So the user program is converted into this device location-agnostic pathways, intermediate representation, or IR. It's expressed as a custom MLIR dialect.
And the key innovation for scalability is the single node representation.
Right, so if you have a computation that is sharded across another or devices, Pathways represents that entire sharded computation with a single node in the data flow graph.
That's a profound structural difference from the older model. It doesn't matter I split my computation 10 ways or 10,000 ways, it still only consumes one node in the high-level coordination graph.
Correct. And this entirely bypasses the null times null edge explosion.
Right.
When you connect computation A, which has n shards, to computation B, also with n shards, there is only one logical edge between the two logical nodes. This compact representation, it drastically reduces the overhead associated with graph serialization, execution planning, and just the total memory footprint required to manage thousands of cores.
Which is essential if you want to do real-time orchestration at that scale.
You have to have it.
So managing that scale and coordinating communication across thousands of cores and multiple physical islands, that requires an incredibly robust coordination substrate. I understand Pathways didn't build this from scratch. They relied on something called Plaque.
Yes. Plaque is the existing closed-source production sharded data flow system that Pathways adopts for all of its cross-host coordination using the data center network.
So it's the reliable communication and control backbone.
It is. It's the engine underneath.
What architectural guarantees does Plaque offer that make it suitable for the unique demands of Pathways and, future ML research?
It has to meet 4 critical requirements. First, the compact representation we just discussed, that single node per sharded computation.
Okay.
Second, and this is absolutely vital for supporting future sparse models, PLQE has to support sparse data exchanges along those sharded edges.
Let's elaborate on sparse exchange.
Yeah.
Why is that feature non-trivial to implement at scale?
Well, in a dense SPMD system, if computation A talks to computation B, every shard of A talks to every shard of B, or at least every shard knows exactly which neighbor it needs to connect to.
It's all preordained.
It is. In a scarce exchange, an edge between 2 sharded computations means messages are only sent between a dynamically chosen subset of shards.
Ah, and the decision of who talks to whom is made mid-execution based on the router's output.
Exactly. So PLQ must be able to manage these dynamic, fine-grained messages and track their progress efficiently, even when it's dealing with potentially thousands of simultaneous transient connections.
So it has to manage communication that is highly variable in volume and location, all in real time.
All in real time. The third requirement is speed and throughput.
Right.
PLIQE has to deliver critical control messages, like scheduling commands and data handles, with very low latency, because these are in the critical path for feeding the accelerators.
But it also has to handle big data transfers.
Simultaneously,
Yeah.
it has to efficiently batch messages destined for the same host when high throughput is required for large data transfers.
And the fourth requirement.
PLIQ has to serve as a general-purpose engine for all the background housekeeping tasks,
Like what?
monitoring the health of devices, distributing configuration updates, and delivering robust error and failure signals across the entire distributed system.
So this robust pre-existing coordination foundation allows the Pathways architecture to confidently rely on this asynchronous distributed data flow model without sacrificing essential resilience.
It's the bedrock.
So they built an efficient, scalable graph representation layer, married it to a centralized, flexible resource manager, and bolted it onto a proven production-grade coordination backbone. The stage is set. Now we move to the engine, the algorithms that actually deliver the speed.
This is where it gets really interesting. The architectural choices, they enable the complexity, but the performance is truly delivered by the 2 key algorithms, gang-scheduled dynamic dispatch and parallel asynchronous dispatch.
Let's start with gang-scheduled dynamic dispatch. Why is centralized gang scheduling a mandatory feature for complex ML systems, especially on non-preemptible hardware like TPUs?
The source material is adamant about this. TPUs are single-threaded, and they run non-preemptible kernels.
Meaning once a kernel starts, you can't interrupt it.
You can't. So if you have any computations that rely on communication, and all large-scale ML training does, the system will experience deadlock if those communicating kernel computations are not enqueued in a globally consistent order across all the participating devices.
Right. If device X starts waiting for data from device Y, and device Y hasn't even had the instruction to produce that data scheduled yet, everything just freezes.
Precisely. To prevent this catastrophic state, Pathways enforces order using a centralized scheduler per island.
One for each island.
One for each island. And this scheduler consistently orders all computations submitted across all programs running on that specific island.
And PIL-AQE helps with this.
The PLAQ dataflow program is what works with it. It does three things. One, it enqueues local compiled functions with what are called buffer futures as inputs.
So, placeholders for data that will arrive later.
Exactly. Two, it enqueues network sends for the buffer futures that are outputs. And three, it communicates with that centralized scheduler to ensure consistent ordering across all the concurrent programs.
Okay, but a centralized scheduler managing potentially thousands of cores inherently introduces a risk of fragility and latency.
It does.
What measures prevent this single point of control from becoming the system's biggest bottleneck?
That's an excellent critical point. This system would absolutely fail spectacularly if it relied on synchronous communication with that centralized scheduler. And that is where the second core innovation comes in: parallel asynchronous dispatch. This mechanism is designed explicitly to mask the latency and overheads that are associated with centralized control.
We need to understand the sequential bottleneck first. How did traditional asynchronous systems fail to keep the accelerator fed?
If you look at Figure 4a in the sources, you see that in a traditional asynchronous system, all the host-side work was performed sequentially.
Okay.
Host A finishes its kernel, the results are transferred across the network, and only after the results finally land does host B begin its own host-side work: the scheduling, the resource allocation, the preparation for its successor node.
The pipeline stalls if the host-side preparation time is longer than the kernel execution time.
And often it is, especially when you have cross-DCN latency involved.
Hmm.
If the on-device computation, let's call it A, is short, the pipeline stalls because the host-side orchestration and control path, that becomes the critical bottleneck.
So you're just sitting there waiting on DCN latency and host-side processing before the next stage can even be prepped and submitted to the scheduler.
You're just burning cycles.
So how does parallel dispatch exploit the architecture to fix this?
It exploits the fact we mentioned earlier, that these compiled functions have statically known resource usage, including their input and output shapes.
So the system doesn't need the final data results to start preparing the next step.
Exactly. The parallel dispatch design runs most of the host-side preparatory work for a successor node in parallel with the predecessor's computation.
Whoa, that's a massive optimization. You're overlapping the orchestration latency, the DCN communication, the scheduler interaction, the resource allocation with the actual high-speed accelerator computation time.
That's it. The moment a predecessor is submitted, the system can speculatively start prepping the successor's data structures and interacting with the centralized scheduler.
So it dramatically amortizes all those fixed client and scheduling overheads, making the DCN latency penalty virtually invisible for any sufficiently large task?
That's the goal. It just disappears into the execution time.
If you are prepping the host-side work for the successor before the predecessor is finished, doesn't that require a significant upfront investment in host memory to hold all those speculative structures, like the buffer futures and intermediate IR definitions?
It does require sophisticated memory management, which we'll talk about in a moment, but the trade-off is deemed highly worthwhile.
Okay.
And furthermore, there's an optimization related to communication, when a substantial subgraph can be scheduled statically.
Meaning it consists purely of regular compiled functions without any dynamic control flow?
Correct. When that's the case, the program sends a single message describing the entire subgraph to the centralized island scheduler.
One message replaces potentially hundreds of separate scheduling requests.
Yes, and it minimizes network traffic dramatically. But crucially, the scheduler receives this single message, but doesn't have to enqueue the entire subgraph as one monolithic block.
Oh, that's clever.
It can still interleave the individual computations with other concurrent programs, which ensures fair resource sharing while maintaining high efficiency.
This all hinges on managing intermediate data efficiently. Since the data is flowing asynchronously, potentially across islands, how does Pathways manage the buffers and memory?
It uses two dedicated concepts. First, The sharded buffer abstraction.
Okay.
Just as a sharded computation is a single logical node, a buffer that's distributed over multiple devices is treated as a single logical buffer.
And this allows the client to scale much faster.
It does, because the bookkeeping costs like reference counting, which is necessary for garbage collection, are amortized at the granularity of the logical buffer, rather than tracking every individual shard buffer across hundreds or thousands of devices.
Less overhead for the client equals faster overall performance. And second, the object store. It must be tailored specifically for the accelerator environment.
Correct. Each host manages a sharded object store. This store is similar in concept to high-performance distributed memory systems you might see elsewhere, but it's specifically extended to track buffers held in the accelerator's high bandwidth memory, or HBM.
HBM. That's the precious limited resource right on the chip. It's expensive, high speed, and it defines how large a model can actually fit.
And because HBM is so critical and so scarce, tracking its usage meticulously is essential. Intermediate values are kept in these object stores while they're waiting for transfer or for a subsequent computation. The system tags these objects with ownership labels for robust garbage collection, and more importantly, it implements back pressure.
Back pressure.
So if computation is trying to allocate memory, but the HBM is full because other programs' intermediate results are occupying it, the object store can actually stall that computation until space is freed.
That level of fine-grained, accelerator-specific memory management is non-trivial, but it's vital for high-density multi-tenancy.
You couldn't do it without it.
So the architecture relies on this deep vertical control, a single compact graph, centralized resource management, and specialized HBM-aware object stores, all moving in parallel with the goal of hiding network latency. But theory has to meet the brutal reality of the benchmarks. The ultimate technical question Pathways faced was, can we combine the flexibility of a single controller with the raw throughput of a dedicated multi-controller SPMD system? The performance validation seems to show they successfully masked the overheads of centralization.
They did.
Let's start with the micro benchmarks. Where does the single controller model naturally lose?
Well, for trivial, absolutely minimal computation, say a single scalar, all-reduce operation multi-controller JX is naturally going to be faster.
And why is that?
It's simply because Pathways still requires that DCN message dispatch for control. And however asynchronous it is, it's still slower than JKEX's local PCIe control path. That initial DCN penalty just dominates the execution time for these negligible workloads.
That makes perfect sense. The cost of the DCN control message is a fixed overhead. But the crucial finding is how quickly Pathways reaches parity.
Yes. The finding is that once you have enough work that's fused into a single compiled function node, the Pathways single controller overheads become negligible.
They just disappear.
They do. They match JX's throughput performance even when scaling up to 1,000 TPU cores.
Okay, give us the numbers that define the boundary of acceptable overhead. What's the tipping point?
The sources show that for a system of 16 hosts, so 128 TPUs, Pathways achieves parity with JX for computations lasting only 2.3 milliseconds.
Okay, 2.2 milliseconds. Is that a lot in this world? How should I think about that number?
It's very, very short. And when they scaled the system significantly to 512 hosts, so 2048 TPUs, the parity point rises to 35 milliseconds.
So for any realistic modern ML training computation, which often involves operations lasting seconds or tens of seconds, these dispatch overheads are entirely masked.
Completely absorbed. Anything longer than that, and they match the fastest available system. The centralized orchestration cost is just absorbed by the sheer amount of work the accelerator is performing.
Now let's analyze the benefit of the parallel asynchronous dispatch innovation. This was designed specifically for these pipeline models. How much of a performance gain did it offer?
The benefit is significant, and it grows with complexity. They tested a workload where pipeline stages, each residing on a different host, were chained together. When comparing the traditional sequential asynchronous dispatch from Figure 4a versus their parallel approach in 4b, the parallel dispatch dramatically improves performance, especially as the number of stages increases, say, going from 4 stages up to 16 stages.
This suggests it minimizes the pipeline bubble, that idle time between stages.
It does. The parallel preparation keeps the accelerators continuously fed by overlapping those host-side fixed overheads with the execution time.
Right.
If the host has to wait sequentially, that latency gap becomes this massive bubble that just drags down the aggregate throughput of the entire pipeline. Parallel dispatch shrinks that bubble to almost nothing.
Okay, let's turn to multi-tenancy. Centralized control was supposed to enable sophisticated sharing. How efficient is Pathways at switching between different client programs?
It's highly efficient. Pathways demonstrates its ability to time multiplex accelerators between concurrent programs submitted by different clients.
And crucially, the source material explicitly notes there is no overhead to context switch between programs from different clients.
Provided their resources, specifically their intermediate buffers, can fit concurrently within the accelerator's high bandwidth memory.
Zero overhead context switching between separate complex workloads is incredible, especially considering the level of global coordination required.
This capability is a direct result of that centralized resource manager and the non-preemptible gang scheduling.
Mm.
Because the system controls the resource allocation globally, and because execution order is strictly enforced by that centralized island scheduler, it can guarantee performance isolation and enforce proportional share.
Right, I saw that. Figure 9 shows traces where the scheduler successfully enforces ratios like 1.2.4.8 for gang-scheduled concurrent programs submitted by 4 different clients.
It works.
Yeah.
This provides robust fairness and isolation, which is a major leap forward for cluster management in research environments.
Now for the ultimate technical triumph. Scaling across those heterogeneous islands connected by the slower data center network. Older multi-controller systems like JAX were typically restricted to a single island, limited by the ICI.
Right.
Did Pathways successfully bridge that gap?
Yes, and this is probably the most remarkable validation point in the whole paper. Pathways is the first system designed to transparently and efficiently execute programs spanning multiple TPU pods or islands connected over the slower DCN.
And the key is that it achieves parity performance.
It does.
How much degradation did they actually see when using the slow DCN highway instead of the fast ICI local street?
Okay, so for a 3 billion parameter transformer model trained using a 16-stage pipeline, they recorded a throughput of 131.4K tokens per second.
Mm.
The critical finding is that they achieved the exact same throughput, 131.4K tokens per second, whether they used a single massive homogeneous island of 128 cores connected via the fast ICI or 4 separate islands of 32 cores, each connected exclusively via the slower DCN.
Wait, let me get this straight. They fully mask the difference between the high-speed internal interconnect and the general-purpose data center network.
They did. The DCN transfers, the slower cross-island communication, were effectively and aggressively overlapped with the computation. It means the parallel asynchronous dispatch mechanism successfully hid the physical latency of the DCN.
That is the definitive proof of concept. The single controller model, with its parallel asynchronous dispatch, is capable of leveraging cluster resources in a way that overcomes physical limitations that previously constrained distributed ML.
They even scaled this test further. They trained a colossal 136 billion parameter model over 2 islands connected via DCN.
Okay.
And the system achieved approximately 97% of the throughput compared to running the same job on a single, much larger island.
Why the 3% difference? Does that 3% represent the unavoidable tax of the single controller flexibility?
I think so. It represents the hard limit of what can be masked. While they achieve this incredible overlap, there are unavoidable initial setup latencies and coordination steps that still have to travel over the DCN.
Sure.
But achieving 97% efficiency while unlocking the ability to scale to arbitrary numbers of islands, a capability that was previously locked away, is a phenomenal engineering compromise. It validates that Pathways successfully marry centralized flexibility with the highest standards of decentralized performance.
So Pathways wasn't built merely to run today's models slightly faster. It was designed to unlock future ML research ideas that current SPMD systems just cannot touch. Let's look at what the flexibility inherent in this architecture grants users, moving beyond that restrictive lockstep model.
Well, the first major gain is unprecedented scalability for existing frameworks. By communicating transparently and efficiently over both ICI and DCN, Pathways allows frameworks like JAX, which were previously restricted to single TPU pods, to scale for the first time across multiple pods containing thousands of cores. This just opens up entirely new frontiers for model size.
And most importantly, it naturally supports non-SPMD models, the kinds of models that are probably going to define the next decade of AI.
Yes, including the deeply pipelined models we discussed, and critically, those that rely on computational sparsity. The architecture's design anticipates the needs of these future models from the ground up, starting with the Plec-We coordination layer.
Let's focus on that ultimate goal, data-dependent, vectorized control flow. Why is this the bleeding edge, and how does Pathways make it practical?
As models grow larger, approaching a trillion or more parameters. The current practice of updating every model weight based on every example and every training step becomes catastrophically wasteful.
In terms of energy, in terms of compute time.
Both. Future models have to employ true sparsity. They need this fine-grained control flow where model weights are updated per example or even per subexample, like a single sentence or a patch of an image.
So this means the system has to decide, based on the input data itself, which specific parts of this massive model architecture to activate.
That's the essence of models like mixture of experts. They require routing subexamples to different specialized accelerator subsets based on learned functions.
And this routing demands efficient, fine-grained, data-dependent data exchanges between nodes. Traditional SPMD just can't handle this dynamic conditional communication.
It can't.
But pathways can, specifically through the implementation of sparse data exchange in that Plex substrate.
Precisely. The system was designed with that capability built in from day one. Plaque's ability to manage high fan-out, fan-in communication, where only a subset of shards is active and communicating dynamically, makes the fine-grained routing required for sparsity feasible at the scale of thousands of cores.
So pathways is the system layer that makes trillion-parameter sparsity practically scalable and, well, researchable.
That's the idea.
And finally, let's revisit the implications for cluster management. The single controller design and the global resource manager, they allow for much more sophisticated policies than were ever possible when control was decentralized.
This is a major systemic consequence. Because the system maintains a consistent global view of resource consumption and execution status across the entire cluster, it permits the reintroduction of sophisticated cluster management policies that can operate at very small timescales.
We're talking milliseconds?
Milliseconds.
Right.
And they govern orders of magnitude larger pools of resources, including thousands of cores and terabytes of HBM.
So what critical features are now possible because of this centralized high-speed control?
Well, we're talking about performance isolation, ensuring that one client's resource-intensive job doesn't degrade the latency or throughput of a second client's job.
Sure.
We're talking about comprehensive access control and meticulous resource accounting, which is essential for managing the sheer cost of these large clusters.
And perhaps most importantly, dynamic elasticity.
Yes, allowing the resource manager to add, reclaim, or migrate virtual devices transparently without requiring the user program to be restarted or even paused.
This really moves machine learning infrastructure from being a brittle, exclusive environment to a dynamically managed multi-tenant cloud service. It's a complete vertical integration from the hardware abstraction layer right up through the cluster scheduling policies, all enabled by rethinking how the data flow graph is managed and dispatched.
The Pathways project. It successfully married the flexibility of older single-controller systems with the raw speed of modern multi-controller frameworks by leveraging asynchronous distributed data flow and parallel dispatch. It is proven performance parity on existing SPMD models while delivering the structural capabilities necessary for these highly complex, sparse, and heterogeneous workloads that rely on dynamic routing.
So what does this all mean for you, the learner? The system mechanisms, sharded data flow, centralized scheduling, and parallel dispatch are now validated as fast, scalable, and flexible. It's not just an incremental improvement in speed.
Not at all.
It's a solid basis for research into novel policies that could genuinely unlock the next generation of massive, sparse, and complex AI models. The era where hardware alone solved the scaling problem is over. System software like Pathways has to evolve to meet the structural demands of future model complexity.
That is the core takeaway. The engineering has proven its worth.
And here is a final provocative thought for you to consider. The source material mentions that almost all current ML models update every model weight based on every example in every step. If systems like Pathways successfully enable widespread use of fine-grained, data-dependent vectorized control flow and computational sparsity, allowing only a tiny fraction of its weights to be activated for any given task. What will the 100 trillion parameter model of the future look like, and how radically will that shift change the entire economics of training and deployment?
Something to chew on until our next deep dive.
Thanks for joining us for the deep dive.